Hey everyone, we are Group 8. In this presentation, we will share our project titled A Transfer Learning Based Medical Visual Question Answering Framework for Data Scarce Radiology using pre-trained vision language models, where we evaluate how well transfer learning and pre-trained vision language models perform when labeled radiology data is limited. In this presentation, we will walk through the introduction, objective, literature review, methods and research design, final results, key findings with limitations and future improvements, and finally, our conclusion. Medical Visual Question Answering, or MAD-VQA, answers clinical questions using a medical image, which supports interactive radiology queries beyond image-only classification. However, in radiology, labeled question-answer data is limited and costly, which makes models prone to overfitting and weak generalization. At the same time, MAD-VQA performance can vary across question types because vision language alignment is not always learned reliably. This leads directly to our project focus, which is to evaluate how well different transfer learning strategies handle closed-ended versus open-ended questions in the data scarce setting. Based on that motivation, our goal is to develop and evaluate a transfer learning based MAD-VQA framework for radiology under data scarce conditions. We plan to implement two approaches. The first is a baseline CNN plus LSTM model to establish a benchmark. The second is a pre-trained vision language model approach, so we can test whether transfer learning improves performance, especially across different question types. The literature supports this comparison because many MAD-VQA studies start from strong baseline pipelines, then improve performance using better fusion, prompting, or knowledge grounding strategies. However, three gaps consistently appear. Robustness remains limited in low data settings, especially for open-ended questions. Second, many reported gains add complexity that reduces reproducibility. Finally, VLM-based MAD-VQA can be brittle because outputs may depend heavily on prompting or external knowledge quality. These gaps justify a controlled fair baseline versus VLM comparison, so we can isolate what improves performance and where failures still remain. With those gaps in mind, we use VQA RAD, which contains radiology images paired with clinician questions and answers, covering both closed-ended and open-ended formats. To ensure fair comparison, both models share one standardized pipeline that cleans and normalizes question-answer tags, pre-processes images, and creates fixed seed splits balanced by question type. For the baseline, we use ResNet50 to encode images and BLSTM to encode questions, then fuse features and predict with separate heads. For the VLM approach, we use a BLIP2 style pre-trained backbone with prompting, and we plan LoRa adaptation for efficient fine-tuning. Following our flowchart, we run dataset preparation, baseline benchmarking, VLM evaluation on the same split, and finally deeper analysis with iteration. To evaluate both models consistently, we report results separately for closed-ended and open-ended questions. For closed-ended, we report accuracy and F1 score to capture yes-no reliability beyond simple correctness. For open-ended, we report exact match and token level F1 to reflect partial answer overlap when wording differs. We then review common error patterns and run basic robustness checks before finalizing the results and linking the findings back to our research questions and objectives. For the training setup, we fix reproducible settings for the baseline so that the experiment can be repeated reliably. We use a random seed of 42, resize all images to 224 by 224, and truncated questions to a maximum length of 30 tokens. We also constrain the answer space to the top 100 most frequent training answers which makes the baseline a controlled classification setting. Training uses cross-entropy loss with the Adam optimizer, and we select the best checkpoint based on the highest validation overall exact match, saving both the checkpoint and the training history to the outputs folder. For BLIP, we use Salesforce BLIP VQA base with the official processor and pre-trained weights. We cap inference deterministic by using beam search for open-ended questions and disabling sampling, and for closed-ended questions, we applied a yes versus no rule using loss comparison. Finally, we applied the same answer normalization steps and evaluated BLIP on the same cap test indices as the baseline, so the comparison is fair. For evaluation, the key point is that the baseline can only predict within its top 100 answer vocabulary. To avoid an unfair comparison, we filtered the test set and kept only samples whose normalized ground truth answers fall within that baseline vocabulary. This produces a filtered subset of 319 samples with 251 close-ended and 68 open-ended questions, and we run BLIP on the exact same cap indices. In terms of metrics, close-ended questions are evaluated using accuracy, and we also report precision, recall, and F1 for the yes class together with confusion matrices to show false positives and false negatives. For open-ended questions, we report exact match for strict correctness, and we include token F1 and Roach L to capture partial overlap when predictions are close but not identical. Looking at the final results, the supervised baseline achieves higher overall exact match than prompt-only BLIP. The close-ended gap is smaller, but the open-ended gap is very large and dominates the overall difference. This suggests that a supervised model trained with a constrained answer space can still perform reliably in a data-scarce setting, while a general pre-trained VLM without domain adaptation struggles to produce the exact short clinical term required for open-ended answers. This summary is why we then look deeper into training behavior and error patterns to explain where each model succeeds or fails. The training curves show stable optimization, where training loss decreases smoothly across epochs. At the same time, validation overall exact match improves early and reaches a clear peak, which motivates checkpoint selection rather than simply taking the last epoch. We chose the checkpoint at the peak validation overall exact match to avoid later degradation. We also observed that validation and test trends are not perfectly aligned, which reinforces that validation-based checkpointing is important for fair and reproducible reporting of the baseline's final performance. When we separate results by question type, close-ended remains consistently easier than open-ended throughout training on both validation and tests. Close-ended accuracy stays relatively stable with modest variation, while open-ended exact match improves more gradually and remains lower overall. This fits the task because open-ended questions require more precise grounding and terminology rather than only a binary decision. The key takeaway here is that question type explains a large portion of performance variance, so reporting close and open results separately is necessary for a meaningful comparison. Next, we examine confusion matrices because accuracy alone can hide important behavior. The confusion matrices show that BLIP predicts yes much more often, which indicates a bias toward positive findings. That matters because higher false positives correspond to incorrectly asserting abnormalities. In contrast, the baseline is more conservative, which reduces false positives, but it can still miss some positives. Overall, this slide motivates why we include confusion matrices and bias checks as part of the close-ended evaluation rather than relying on accuracy alone. For open-ended answers, we examine token F1 and roach L distributions to understand whether errors are minor wording differences or truly off-target outputs. The baseline concentrates near high overlap, while BLIP concentrates near zero overlap, and both metrics show the same separation. This confirms that BLIP prompt-only outputs frequently miss the expected short clinical answers substantially, rather than being slightly different in phrasing. The takeaway is that the open-ended gap reflects grounding and terminology alignment issues, not only strict exact match scoring. We also check whether question complexity affects correctness using question length. For the baseline, wrong predictions tend to occur more often for longer questions, which suggests sensitivity to increased linguistic complexity. For BLIP, correct and wrong cases overlap strongly by length, so length is not the main driver of its failures. This suggests that baseline improvements may benefit from stronger question encoding and reasoning capacity, while BLIP improvements would require radiology alignment, such as adaptation or stronger output constraints. And finally, we summarize common failure targets by looking at the most frequent wrong ground truth answers. Both models often fail on short high-impact tokens like yes and no, as well as laterality or view-related terms. The baseline errors reflect yes and no flips and left versus right confusion, while BLIP tends to default to frequent generic outputs, especially no. These patterns show where reliability breaks down in clinically sensitive categories, and they directly motivate future improvements, such as laterality-focused fixes, better calibration for binary decisions, and domain adaptation for the pre-trained model. Putting the results together, 3 link points emerge. First, the supervised baseline leads overall on the filtered VQA-RAD subset, with higher exact match than BLIP in the zero-shot setting, and the most direct reason is that BLIP was not adapted to the radiology domain. This makes LoRa-based fine-tuning the most actionable next step to improve alignment and open-ended answering. Second, open-ended questions are the dominant bottleneck because the largest performance gap appears there, and BLIP frequently produces outputs with very low overlap to the ground truth. Since exact match is strict for short clinical answers, we will strengthen normalization and add semantic aware metrics to better reflect clinically equivalent wording. Third, close-ended analysis shows different decision bias, where BLIP tends to overpredict yes and introduces more false positives, while the baseline is mildly conservative. To improve reliability, we will prioritize error-driven fixes and calibration, focusing on recurring failure modes such as yes or no flips, laterality swaps, and big visual grounding across question types. In conclusion, MAT-VQA in data-scarce radiology remains challenging, and the hardest part is open-ended questioning. Our work delivers a reproducible comparison between a supervised ResNet50 plus BIL-STM baseline and a pre-trained BLIP VQA model evaluated on the same filtered subset and metrics. The results show that the baseline is more reliable overall, while prompt-only BLIP struggles most on open-ended answers, which points directly to the need for domain adaptation and improved open-ended evaluation. Ultimately, this supports SDG 3 by strengthening trustworthy clinical question answering and supports SDG 9 by advancing more reliable healthcare AI innovation. Thank you for your attention. That concludes our presentation on transfer learning based MAT-VQA in data-scarce radiology.